Greetings to all. First of all, thanks to organizer committee for giving me a chance to deliver a small lecture in front of delegate person through online mode during the COVID situations. Myself, Chatterjee. Now, I'm going to share my share screen. Hopefully, all of you see my share screen. Today, the title of my paper is Comparative Study on Stochastic and Deterministic Approach in Marine Plankton Ecosystem Model-Based Study. These are the outline in my paper. So before going into details of our mathematical model, I just give some small introduction first. We all know that plankton may broadly classify into two groups, like phytoplankton and zooplankton. And phytoplankton, known as microalgae that require sunlight in order to live and grow, as well as the zooplankton, the animal that consume phytoplankton, which in turn are eaten by larger organisms. So what does plankton do for our Earth? Plankton do huge service for our Earth, like supply food for marine life, supply oxygen for human life, etc. So one of the most important features of an ecosystem is the number of species in different trophic level of a food web. And also, the living organism gradually grow and actively incorporate energy and nutrient into their biomass of their descendant. And this nutrient are obtained by either uptaking from abiotic environment or consumption from the biomass of other organisms in the food web. What is a planktonic bloom? A planktonic bloom is defined as a rapid and marked increase in the local population of a plankton. The main factor that causes bloom to occur are sunlight, nutrient, and change in water temperature. Now we have to see the comparative study between the deterministic and stochastic model. In deterministic model, the outcome of the model is fully determined by the parameter values and the initial conditions. But on the other hand, stochastic model processes some inherent randomness. The same set of parameter values and the initial condition will lead to an ensemble of different outcome. And stochastic model can be developed into two ways. Like firstly, to develop the stochastic system, we can replace one of the environmental parameter by some random parameter in the deterministic model. Secondly, without altering any particular parameters in deterministic dynamic equation, we can add a randomly fluctuating driving force. To construct our mathematical model, we consider some basic assumptions. Firstly, we consider a TPP zooplankton interaction model. TPP means that is toxin producing phytoplankton with predator response taken as a monotonically increasing function up to a certain threshold density and then monotonically decreasing. We also assume the predation rate to be a Honin type 2 functional response because in reality, the grazing function is subject to saturation, so that some TPP escape from predation by zooplankton and from a tide. The prey is assumed to detect the presence of the predator and to respond by grouping together and releasing toxin chemical, which diffuse in the surrounding water through the surface of the patch. Here we also assume the patch size to be proportional to the phytoplankton density. This is the symmetry diagram of our model. Here, this is the nutrient, that is N. Phytoplankton, we denoted by P, and zooplankton, we denoted by Z. Here, alpha 1 is the uptake rate of a nutrient, alpha 2 is the conversion rate of a nutrient, so alpha 1 greater than equal to alpha 2. Here, C1 is the predation rate of phytoplankton by the zooplankton, and E is the conversion rate. Here also K1, K2 are the half saturation constant. Here D is the dilution rate of a nutrient. N0 is constant nutrient input. Here mu1 and mu2 are the motor rate of phytoplankton and zooplankton respectively, as well as mu3 and mu4 are the recycling rate due to death of phytoplankton and zooplankton. So mu1 greater than equal to mu3 and mu2 greater than equal to mu4. Here rho is the degree of toxicity and here K is the fraction part of phytoplankton which aggregate to the patch. This is our mathematical model. I have already mentioned all the components and parameter. So under this initial condition, we first find the equilibrium point of a system. Here you see the three equilibrium point. Firstly, the plankton free equilibrium, that is E0, where E0 is N0, 0, 0. Secondly is geoplankton free equilibrium, that is E1. This is the value of N1 and P1. And this is the existence criteria for E1. And now we have to study the positive interior equilibrium, where this is the value of Z star. And from this equation, we get the value of P star by numerical simulation. And putting the value of Z star and P star in equation 1, we got the value of N star. So if this condition satisfied, the interior equilibrium is exist. Now we have to study the stability analysis of a system. So first we compute the Jacobian matrix like this, and stability of E0 is then ensured if R0 less than 1, and this is the value of R0. And there exists a feasible geoplankton free steady state E1, which is unstable if this condition is satisfied, which is given from the Jacobian matrix. And now we study the stability analysis at E star. And so first we compute the Jacobian matrix at E star like this. And these are the components. From this Jacobian matrix, we first compute the characteristic equation like this. And this is the value. And according to Raoult-Harris criteria, we say that if this condition satisfied, then E star is locally asymptotically stable. Next, we study the Hopf bifurcation of a system. So here you see when the constant Newton input, that is N0, crosses a certain critical value N0C, then the system enter into a Hopf bifurcation around the positive interior equilibrium, which induces oscillation of the populations. And next, we derive the reaction of Hopf bifurcation. So after some calculation and simplification, we find the value of first Lyapunov coefficient. And if this condition satisfied, then Hopf bifurcation will be supercritical. Now we have to study the stochastic model. So first we develop the deterministic model by applying Gauss white noise type stochastic perturbation, and then the stochastic model convert into like this, where sigma 1, sigma 2, sigma 3 are the intensity of environmental fluctuation, and JIT are the standard winner process independent to each other. And this equation can be written as Ito stochastic differential equation of the type this. Here G is the slowly varying continuous component and drift coefficient, and G is the rapidly varying continuous random component or diffusion coefficients. And here this is the value of G, this is the value of F. I'm not going into details of the mathematical calculation parts. Now we consider the Lyapunov function, and after some calculation and simplification, we find the three conditions. This is sigma 1 square, sigma 2 square, and sigma 3 square. And if this condition satisfied, then we can say that the system for is asymptotically mean square stable. Now we study the numerical simulation of the system. So first we choose the given set of parameter values. And for the given set of parameter values, we see that the system is locally asymptotically stable at E star. Now we vary the parameter N0. Here you see this is the Hopf point and this is the branch point. Here you see that when constant input is increasing, then the system shifted to stable to unstable behavior. And when we decreasing the value of N0, then we see that geoplankton goes to extinction. And here, this is the bifurcation diagram for N0. Similarly, we draw another figure for D. And I have already mentioned this is the Hopf point and this is the branch point. And this is the bifurcation diagram for D. Next, we plot another three figures with respect to mu2, that is moderate rate of zooplankton, and this is the bifurcation diagram for mu2. And further we study the another three bifurcation diagram for mu1, rho, and k. And this is the family of a limit cycle bifurcating from the Hopf point for rho. Next we study the two parameter bifurcation diagram for N0D, N0 mu1, N0k, and N0 rho. And here we study the stable zone and unstable zone. Now we study the stochastical system. by numerical simulation. So first we choose the given set of parameter values, and here you see this system is stochastically stable. But when you choose the value of sigma 1, sigma 2, sigma 3 like this, then we can say that the system is stochastically unstable. And this table represents the nature of the equilibrium point. I have already mentioned all the sensitive parameter and find the result. So throughout the study, we see that the phytoplankton and zooplankton will die out due to low value of constant nutrient input N0, but stable equilibrium switches to oscillatory behavior around Easter for high value of N0. Also, here we see each species will oscillate for high value of dilution rate of nutrient. Low value of mu1 and mu2 may lead to oscillatory behavior around Easter. On the other hand, high value of mu1 and mu2 may lead to zooplankton free equilibrium separately, and the system shifted to unstable behavior in presence of low value of amount of toxicity. And it is observed that for low value of noise intensity lead to stochastic asymptotic stability of the system but slightly higher value of noise intensity may lead to oscillation with high amplitude. And it is clearly indicate that our model system persists stochastically stable. It satisfies suitable conditions which involve both the maximum size of the environmental random fluctuation as well as model parameter. These are the reference. Thank you.